All right, get ready, everybody. We're diving deep into lithium-sulfur batteries today. Some fascinating research landed on our desks about a new way to boost their performance.
Hmm.
And it all starts with something called ball milling.
Oh, yeah, I've heard about this.
Have you?
Yeah. Ball milling is making quite a splash in battery research.
Pun intended.
Maybe.
Yeah.
It's a really simple technique,
Okay.
but it could really shake things up, so to speak.
Okay, I like where this is going. But for our listeners who haven't heard about this, why are lithium-sulfur batteries such a big deal anyway?
Well, because they have the potential to store a lot more energy
Okay.
than the lithium-ion batteries we use in our phones and laptops today.
So,
We could see electric vehicles with much longer ranges and even grid-scale energy storage that could change how we use renewable energy.
okay, so more energy, longer ranges, greener future. It sounds like, the dream battery. What's the catch?
Well, the problem is the chemistry.
Oh,
The reactions inside these batteries can be kind of sluggish. And there's this annoying thing called the polysulfide shuttle effect. So basically what happens is compounds called polysulfides form when the battery is working.
wait,
And these polysulfides can lead to the battery losing performance over time.
gotcha. So polysulfides, those are the bad guys, right?
That's exactly.
How does this research that we're talking about today address these polysulfide problems?
Well, they're using something called covalent organic frameworks, or COFs. It's a way to trap those polysulfides and improve how the battery performs.
Okay.
And that's where ball milling comes in.
COFs, okay. Need a little bit of an explainer here. What are COFs?
So imagine COFs as this really organized, porous material,
Hmm.
like a sponge, but with a really specific repeating structure. The structure gives them a really high surface area, which is perfect for interacting with the battery's active materials.
Okay.
And because they're made from these organic building blocks, we can really customize their properties to fit different applications.
So it's like a customizable sponge, but for batteries.
Pretty much, yeah. And what the researchers found was that if you just ball mill these COFs, you can make them even better at trapping these polysulfides.
Hold on, back up. Ball milling, isn't that just grinding something up?
Yeah, it is.
How does that help a battery?
Well, if you take a clump of flour and break it up into finer particles, you'd have more surface area. Okay? Same principle here. Ball milling breaks the COF into smaller pieces and exposes more active sites, and that makes it better at interacting with the polysulfides.
Okay, so we're making the COF more spongy by grinding it up.
Yeah.
But I think you mentioned that ball milling has different effects depending on what kind of COF you're using, right?
That's right. They tested two types of COFs.
Okay.
One called COF-BTD with small pores,
Gotcha.
and another called COF-TFB with larger pores.
Okay, so what happened?
Well, with COF-TFB, ball milling basically just made it more discreet, like breaking up that clump of flour.
Yeah.
But with COF-BTD, something really interesting happened.
Oh, okay. What happened?
It underwent a total transformation. The rod-like structure of COF-BTD actually rearranged itself into sheets. The researchers called it morphological reconstruction.
Wow, a total makeover.
Yeah.
Okay, that is really cool. But why such a big difference between the two COFs?
It's because of those pore sizes we were talking about. COF-BTD, with its small pores, has stronger interactions between its layers. They're all packed in tighter. This, and also the way its electrons are arranged, makes it more likely to change its shape when it's being ball milled.
Okay, smaller pores, tighter bonds, dramatic transformation. I think I'm getting it.
Yeah.
But I need help connecting the dots here. How do all these structural changes actually make a better battery?
Well, they tested these ball-milled COFs in batteries,
Okay.
and the results are pretty impressive. They found that the ball-milled COF-BTD, or RCOF-BTD, delivered a much higher initial capacity than the unmilled version.
Higher capacity, that's great. So ball milling is like unlocking the COF's potential or something.
Yeah, exactly.
How much higher are we talking?
When they combined it with sulfur, the RCOF-BTD hit 1,429 milliha-Ju1 at 0.1 C.
Okay, 1429. All right, that's a number I can get behind. So we have more capacity. That's great. What else did they find? Was it just a one-time boost, or were there other benefits?
Actually, ball milling did a lot more than just boost capacity. They found that the ball-milled COFs also had reduced polarization. That means there's less resistance inside the battery, so energy can flow more smoothly.
Okay, so less resistance. That's good. That's going to make it more efficient.
Yeah.
But what about the long term? Did that high capacity just fade away quickly?
Nope, that's where the long-term cycling tests come in. The ball-milled COFs were really stable. They kept a lot of their capacity, even after being charged and discharged a bunch of times.
That sounds promising. How much capacity did they retain?
Our COF BTD at S retains 74% of its capacity after 200 cycles at a 0.5 C rate.
74% after 200 cycles. That's pretty impressive. Higher capacity, less resistance, and it lasts a long time. It sounds like ball milling really did the trick.
Yeah.
But what's actually happening inside the battery? How is this working?
Well, to get a better picture of what's going on, the researchers used some fancy techniques to watch the battery in action. One of those was this technique called PITT, which basically measures how much lithium sulfide is forming inside the battery.
Okay, lithium sulfide. Now remind me again why that's so important.
Well, lithium sulfide is one of the products that form when the battery discharges.
Right.
So knowing how it forms and where it goes can give us some clues about how to improve performance.
Gotcha. So what did they learn about lithium sulfide with these ball-milled COFs?
They found that the way lithium sulfide formed changed a bit. In the original COFs, it tended to form on the surface, but in the ball-milled ones, they saw it forming throughout the material.
Interesting. So instead of just sticking to the surface, it's spreading out. Why is that a good thing?
Well, it could mean that the ball-milled COFs are creating more places for the lithium sulfide to form, which can make the battery work more efficiently.
Oh, okay. So it's like a well-organized parking lot for the lithium sulfide,
I like that analogy.
making sure everything's parked neatly and not causing any traffic jams.
Exactly. They also used some techniques to see how easily the lithium ions were moving around in the battery.
Okay, so like checking the traffic flow on those battery highways.
Yeah, and the results were pretty exciting. In the ball-milled COFs, the lithium ions were moving around much more freely.
So a well-organized parking lot and smooth-flowing highways. No wonder those batteries are working so well.
Exactly. It all suggests that ball milling these COFs is making a much better environment inside the battery.
You mentioned that pore size plays a key role here.
Uh-huh.
Can you talk more about that? Why is the smaller pore size in COF BTD so important?
Well, think of it this way. Those smaller pores act like a net, catching and trapping those pesky polysulfides we talked about.
Right, the ones that can cause the battery to lose capacity over time.
Right.
Smaller pores, better polysulfide control, longer lasting battery.
Exactly. It's all about controlling those polysulfides, and the ball-milled COF-BTD, with its smaller pores, seems to be doing a really good job.
This is fascinating. You know, when we started talking about ball milling, I never thought it would be so complicated. But there's one more thing that I'm wondering about. We talked about capacity, resistance, and cycling stability. But what about self-discharge? You know, that thing where batteries just lose their charge even when they're not being used.
Ah, self-discharge. It's definitely something researchers think about when they're working on batteries.
So did they look at that with these COF-modified batteries?
They did, and they found that the ball-milled COFs actually did better at resisting self-discharge
Oh, really?
than the original COF materials.
Even the self-discharge is better.
Yeah.
It's like ball milling is some kind of miracle worker for batteries. What's going on there?
Again, it probably has to do with those smaller pores and their ability to keep the polysulfides under control. By keeping those polysulfides in check, the ball-milled COFs can minimize those reactions that lead to self-discharge.
So to recap, we've got ball milling, this technique that can transform the COFs, and then we end up with higher capacity, less resistance, better long-term cycling, and even reduced self-discharge in these lithium-sulfur batteries. It's almost too good to be true.
It's certainly a promising approach, and while this research focused on lithium-sulfur batteries, this could have much wider implications.
Oh, that's exciting. What other possibilities are you thinking of?
The great thing about this approach is that it's simple and you can scale it up pretty easily. Imagine being able to just change the properties of all sorts of materials by grinding them up in a certain way. This could open doors in so many fields: energy storage, catalysis, sensing, the list goes on.
I'm picturing scientists in the future whipping up amazing new materials using just a mortar and pestle. Okay, before we get carried away with the possibilities, let's go back to those BFT calculations you mentioned earlier.
Oh, right. Those calculations were really helpful in understanding why the ball-milled COFs are so good at trapping those polysulfides.
Okay, I'm ready to dive into the details. For our listeners who aren't familiar with DFT, can you explain what they are and why they're so important?
DFT calculations are basically powerful computer simulations that let us zoom in and see how atoms and molecules are interacting with each other.
Oh.
So in this case, they use DFT to study how a particular polysulfide called Li2S6 interacts with the COF frameworks.
So they're using computer models to see how this Li2S6 molecule behaves around the COFs. That's cool. It's
Yeah.
like getting a microscopic view of what's happening.
Exactly. And what they found is that this Li2S6 molecule is really attracted to certain spots on the COF, specifically near things called enamine bonds and triazine rings.
Okay, enamine bonds and triazine rings. Those are some chemistry terms. Can you remind us what those are?
So enamine bonds and triazine rings, they're just specific arrangements of atoms within the COF structure.
Like,
Enamine bonds, they involve nitrogen and carbon atoms, and triazine rings, those are six-membered rings with three nitrogen and three carbon atoms.
okay, so these imine bonds and triazine rings, they're like little magnets that the Li2S6 molecule is attracted to.
Yeah.
What makes those spots so special? What makes them stand out?
Well, the DFT calculations showed that the Li2S6 molecule, it forms these pretty strong bonds with the atoms near those imine bonds and triazine rings.
Hmm.
They're very drawn to each other.
So it's all about the bonds. The stronger the bond, the better the COF can hold on to those polysulfides.
Exactly. And remember how we talked about those smaller pores in COF-BTD? Well, the simulation showed that those smaller pores actually enhance those interactions even more. It's like they make it even easier for the Li2S6 molecules to get close to those imine bonds and triazine rings.
Ah, so it's a combination of the chemistry and the structure that makes these ball-milled COS so effective. Those DFT calculations really help us understand why these materials are so good at grabbing onto those troublesome polysulfides.
Yeah, they give us that peek behind the curtain.
It's like we have a tiny little detective at the molecular level.
Yeah.
Wow. This has been a fascinating deep dive.
Yeah.
We started with this simple process, ball milling, and we ended up talking about COFs and polysulfides and lithium sulfide and even those cool DFT calculations.
Yeah, it really highlights how we can change materials at such a small scale to get these big improvements in batteries.
I have to say, I'm really impressed with what they've been able to accomplish with a technique as simple as ball milling. Who knows what other discoveries are out there waiting for us?
That's what's so exciting about science. There's always more to learn.
Exactly.
And I think this research is just the beginning for mechanochemistry.
I'm definitely eager to see what the future holds for this field. Well, this has been another great deep dive.
It has.
Thank you for joining me on this journey.
It's been a pleasure.
And to all our listeners out there, stay curious, and we'll catch you on our next deep dive into the amazing world of science.